the mainly just the plus. If it's a plus or minus, I don't get with.
Yeah, no problem. Okay, we'll address those and make sure that we clear those doubts then, Raheel. Okay, so let me just switch my uh, screen here. Let's close that. And oops, we're gonna have to insert that there. And just one moment, Raheel. Okay, there we go. Okay, so share my screen with you here. So the most important thing to understand firstly when it comes to electrolysis is this idea of the reactivity series. Okay, so this one unfortunately has to be memorized. So I'm just going to take a pen here. Of course, what else? Another important thing to know is the reactions of different metals. Okay, so that's almost the starting basis of this. So here I gave you a mnemonic. Do you have another mnemonic that you've been given at school to try and remember the reactivity series?
No, but I think I remember something that's I can't remember.
Something about a zebra,
Yeah,
careless.
yeah, careless.
Okay. So this basically, all right. So this is, so please, yeah, stop for the sodium. Yeah.
Yeah.
Now there is lithium here,
Yeah.
but if you can just remember it to say these are the ones. So these guys here are in group 1. Okay. So with group 1, as with group 2, the reactivity increases, yeah, as you go further down the group. So lithium is found at the top of the group, then sodium, then potassium. Now the reason why the reactivity increases is because the number of shells, okay, around the nucleus of the atom increases as we go down the group, which means then that, so if you imagine an atom, yeah, an atom has got a positively charged nucleus, okay, and then you've got these electrons that are negatively charged. I'm just drawing a simple schematic here because at times you're asked to give a reason why, okay? So if you've got more shells, there's less attraction between the positively charged nucleus and the furthest electron out. So it can easily lose that electron. Whereas the less number of shells you have, in other words, it's a term which we call shielding. So the more shells we have, the more shielded the last electron is from the attraction of the nucleus. Does that make sense? Yeah?
Yeah.
Okay.
Yeah.
So that's what happens as we go down a group. The number of shells or the amount of shielding increases. So if we can remember this, so potassium, sodium, lithium from group 1, and then you've got, and generally for electrolysis purposes, lithium is not a common one, but potassium, sodium you may find. Okay, so that was please stop calling, that's for the sodium, me careless. For the carbon, zebra, instead, it's getting long, try, learn for the lead, try, learn how, copper, it's the easiest one of them because it's the same one, how copper saves gold, okay? So that's just a little bit of a mnemonic. And of course, we've got platinum at the very end. Now, platinum generally and carbon are used as electrodes in during electrolysis. Okay, so carbon and platinum are common electrodes in electrolysis.
So
That is because they're generally what we call inert. Now, inert means they are unreactive. So this guy here and this guy here, platinum.
Why isn't the lithium and platinum in the top?
Well, we could put lithium, but
they're not
generally speaking, you will not see them. So we could put lithium. Now, please stop. Now, what could we use for the L? Please stop. What could we use for the L? Let's get creative here.
uh,
Well, we're going to say, please stop lying, calling me a careless zebra. Why not? Please
so
stop lying, calling me a careless zebra. Instead, try learning how copper saves gold.
please.
No, please, you might confuse it. How copper saves gold pots, maybe. And that's for the platinum. We got there. Okay. So
Yeah,
please
would
stop
they not?
lying, calling me a careless zebra. Instead, try learn how copper saves gold pots.
Okay.
All right.
Would they not ask a question on lithium and platinum with this?
They could, and of course, in your main exam, I've not seen a lot on lithium, but they are absolutely entitled to, because in the same sense that they could ask about sodium, and sodium is in group 1, there's no reason why they might not ask one about lithium. Okay, all right. So that's the main sort of reactivity series anyway here, and unfortunately, it's one of those things that you're going to have to memorize. Not that it will save your life or anything, but it will help you get a good grade on your final exams. Okay, so reactions with oxygen, you're happy, so they burn to form oxides. So these are group 1 and group 2, and we generally call them alkali metals. Okay, so group 1 is alkali metals, group 2 is called alkali earth metals. That's the difference there. So we'll just put a little note here so you're okay with that. So these are alkali metals, and these are alkali earth metals. All right. Reaction with water, important. They react to give off hydrogen, okay? Apart from aluminium, but all these in group 1 and group 2, yeah, they all react and give off hydrogen. Now, one of the things that would generally be asked is, how do you test for hydrogen gas? How do you know that hydrogen gas has been produced? Can you remember how to do that?
Yeah. Is it a squeaky pop test?
Squeaky pop test, of course. Puts out a burning splint with a squeaky pop.
Yeah.
Burning splint with a squeaky pop. I'm going to go into there. Okay.
Yeah.
Now these in group 1 react violently. When you have potassium, it actually produces a lilac flame. That's how reactive it is. And the potassium itself fizzes in the water, or it floats on top of the water essentially. All right. Now the reason why it's worth remembering that, sometimes they do ask, what is observed when potassium reacts with water? Now be very careful when answering a question like that, because they're asking for what is observed. So what is seen, what is felt? So you could of course say, the potassium will float on the water and will produce a lilac flame, yeah, while also giving off a gas. And the reaction vessel gets warmer because it is an exothermic reaction. And of course, you've got energetics involved when we start looking at exothermic and endothermic reactions. But that's not so bad, I think, exothermic and endothermic reactions. The only part maybe we might just have to look at is probably bond energy calculations. Do you remember doing that in chemistry? So where you're given the bond energy of a particular compound, and then you have to work out how much energy is released when it forms certain products. Do you remember doing that?
I don't remember doing that.
Right, it's on your revision list anyway.
Wait,
I will let you know that.
can you like
So
write out one? If
yeah, I can share my screen with you just to show you that it is indeed there. This here. Can you see this part?
bond, I don't remember that.
Okay. Well, the fact that they've given you this page means that
Yeah.
they could include it, and I think there is a huge possibility that they will include a question on bond energy calculations. So we will look at these as well, because this is probably the trickiest part of everything here in energy, under energy changes. Whereas with here, electrolysis is pretty much the whole topic, but it's this extraction of aluminium and also electrolysis of aqueous solutions. This is where it gets a bit muddy. All right, this is not so bad. Likewise, gets a bit tricky on the bond energy calculation. So we'll work through those. All right, now new share, back to the screen. Okay, there was also in the other case as well, zinc, when they react with oxygen, iron, tin, lead, they all form oxides when heated, okay, and the metal powder burns. With water, there's no reaction, worth remembering that, okay. Then reactions with acids. Reactions with acids, hydrogen is produced, all right. Now, in the case of a metal reacting with an acid, there's a general reaction in the general reaction you need to remember is that when you have a metal and an acid, metal plus acid gives salt plus hydrogen. So this is a general one you need to remember. So it could be, I don't know, you could have potassium here as an example, reacting with hydrochloric acid, or the salt that's going to be produced would be potassium chloride. And of course, then you'd have hydrogen H2. So you'd have to balance this equation. Okay. And of course, with these elements, you put the number at the front, which you'll remember just in the same case as you would if you're balancing any equation. Okay, then the ones that do not react, we have these ones here. Okay, these do not react with oxygen, silver, gold, or platinum. Okay, no reaction with water and no reaction with acids either. All right, any questions so far?
No.
Good. All right, the next thing we are going to look at, because again, it brings us into half equations neatly, all right, and it helps us understand half equations a little bit more, are these reactions known as displacement reactions, okay? Ever heard, or can you remember hearing the term a displacement reaction?
I think so, but I'm not sure.
Okay, so as the name sounds, displacement means something is being taken out of its place, isn't it?
Yeah.
So displacement reactions. So to fully appreciate this, we need to revisit our definition of what we mean first. If we have, what do we mean by a redox reaction? So a reaction, and it is a chemical reaction to be very specific, a chemical reaction where reduction and oxidation both take place. Now let's remind ourselves, what is reduction? When we talk about reduction.
Is it gaining? I can't remember. Is it?
No worries, that's fine.
Gaining something. I can't remember.
Yeah, so what we normally use is, well, there's two definitions first to start off with. The easy grade 4 definition is to say that reduction is the removal of oxygen from a compound. And then oxidation is the addition of oxygen to a compound. To form a new compound. Now, these are grade 4 definitions. So they're good for just remembering the general concept at hand. Okay, so we're going to put it as grade 4. But the main one you want to remember is the grade 7 definition. And to remember this, we use something known as oil rig. Okay, so this just reminds us that oxidation is loss of electrons.
Yeah.
Whereas reduction is gain of electrons. So this is the most important one to remember. Oxidation is the loss of electrons. Reduction is the gain of electrons. Okay? You're okay with that one so far? As long as you can remember an oil rig. Right?
I couldn't remember what it was the loss or gain of.
Yeah, oh, right. So in all chemical reactions, it's always, we're always dealing with electrons. It's electrons that are being transferred in any reaction, any chemical reaction. There's no involvement of the nucleus at all. Okay, just purely electrons. All right. Unlike later on in physics, when you look at nuclear reactions do not involve electrons. They involve the nucleus. But we will look at that when we start looking at radioactivity, when we revise for physics, because under radioactivity, you've got fusion reactions that you need to know about.
Fusion. Oh, is that like
that's in physics? So it's nuclear fusion.
Nuclear fusion and fission.
Yeah, correct. So those are reactions, but they involve the nucleus. Whereas all chemical reactions that you learn about just involve electrons. You okay with that? Yeah.
Yeah.
Okay. So let's look at just a simple reaction here, where we have aluminium reacting with iron oxide. Okay. Iron 3 oxide. What is iron 3 oxide? Whenever you see this, what does this mean? Any ideas?
Is it I can't remember. There's something like I can't remember. It was
okay. So what this is trying to tell you is that it is behaving as if it comes from group 3. The iron is. Okay.
Yeah. Yeah.
So iron is what we call a transition metal.
Yeah.
As is aluminium. So they can act as if they've either got 2 electrons or 3 electrons on the outer shell. So in this case, this is behaving as if it's got 3 electrons in its outer shell. Okay. So anyway, this forms. Now, the key question to ask ourselves here is, would aluminium react with iron oxide? Well, to answer that question, this is where the periodic table, knowledge of the periodic table becomes important. So we need to ask ourselves, is aluminium more reactive than iron in the periodic table? And seeing as you are fresh with the reactivity series, I'll give you a little bit of a, it's good for you to see it as many times or as often as possible.
Wait, which one was it? Aluminium and
iron oxide, yes.
So with iron oxide, is it just iron I'm looking at?
It's just the iron you're looking at.
So most reactive. So aluminium is more reactive.
Aluminium is more reactive. So what aluminium will do is it will displace the iron because it's more reactive. So it will kick away the iron. And so now what we get here is we get aluminium oxide and we get iron. Now, this is a common technique actually used when railway lines are being welded together. Okay. So if there's a gap between railings, so they will get a mixture of aluminium and iron oxide, react them together. The iron then forms as molten iron and it fills the gap between rail lines. Okay, so this is quite a popular, it has practical uses, this particular reaction. And so this is what we call a displacement reaction. So in a displacement reaction, okay, a more reactive metal displaces a less reactive metal. Now let's try and look and see what's happening here. We can see that the aluminium has gained oxygen. So what's happened to the aluminium? It's been oxidized. What's happened to the iron oxide?
It's been. Oh, would it be then? It's. Wait, is it what's the opposite?
So you've got the grade 4 definition of.
So. Oh, has it been reduced?
Correct. Because the grade 4 definition says that reduction is the removal of oxygen, and you can see that on the right hand side we've removed oxygen from it. Okay, now we've not involved electrons here, we've just used that basic definition, but we can now of course start involving electrons to start understanding what is going on. So a little bit of a task for you here. Have a go at trying to write the chemical equation for what's just happened in this displacement reaction.
So, like what? As
using chemical symbols.
Oh, that's true.
Yeah.
Wait, do I need my periodic table to this?
You could do, yeah, you could do. You could find it useful. Do you have a periodic table handy?
Yeah.
All right.
Is this supposed to be like where I put the charge on it?
Yes, that's a good technique. Absolutely good technique.
I'm not sure.
It is a bit tricky. Well, I'll give you some pointers how to attempt this, because it's worth having that that technique understood. So okay, aluminium, that's just a metal, so we can just write Al. That's okay, isn't it?
Yeah.
It's this guy here, because we don't know what the formula for iron 3 oxide is. All we know is that because it's iron 3, it's behaving like something with 3 electrons. And somehow it has combined with oxygen. Now, how many electrons does oxygen have?
On its 6.
6, correct. I'm going to use a different color. So this is our oxygen. So you can do it from first principles and say, well, if these are going to react, well, how many electrons from iron does the oxygen need for it to have a full shell?
2.
2, correct. So it can grab this and this here. So I will draw them as they have come from iron in X's form. That leaves me with what? One electron. Yeah?
Yeah.
So the next thing I could do is I could say, well, now we're working at it from first principles here, but I'm going to show you a much easier way of thinking about it. So here's another iron, and here's another oxygen. And again, like before, this one has 6 as well. So it's going to grab, one's going to come from here.
Oh, yeah.
Okay.
Yeah.
And then, of course, now we're also going to get one from here. So this guy's happy. Now, how many do you have left?
Just 2.
2. Fantastic. So what do you reckon I'm going to do next?
Put another, just one more oxygen.
Correct. Spot on. Spot on.
Yeah.
So one more oxygen. There's my oxygen. Those are my outer electrons. And of course, now grab those 2. So we know the formula just by looking at this that it's going to be Fe, I need 2.
Yep.
And how many oxygens? 3. Yeah? So
yep.
we've worked it out. Now that was a bit long.
Yeah.
If you have to do this as an exam, you can do it as a last kind of option if things are not fully making sense, so you can do it that way. But an easier way to do it is to think about this in terms of charges. Yeah. So when the iron loses, so let's imagine it's a metal, isn't it? So what do metals like to do? They like to lose electrons.
Yeah.
All metals, and I'm going to make a point here, so that's worth remembering. All metals like to lose electrons, like to lose outer electrons. And they're doing this so they can achieve the same stability as that of an inert gas like neon or helium. So all the stuff in group 0.
Right.
So when iron loses, if iron loses 3 electrons, what would the charge be on an iron atom that's lost 3 electrons?
Fe 3 plus.
3 plus, correct. Now we're not going to bother with the 3 plus. We're just going to deal with the number. Okay?
Yep.
Then now we're going to write our oxygen next to it. Now oxygen is a non-metal. So what do non-metals like to do in terms of electrons? Do they like receiving or do they like giving?
Receiving.
Receiving, correct. So how many does oxygen need to receive so it gets a full shell?
2.
2, correct. Now what would the charge be if it received 2, just on an oxygen atom?
Wait. Oh, wait. So 2
so if
minus.
an oxygen atom gained 2 electrons, what would the overall charge be?
Oh, it would be 2 minus.
Correct. Now again, as before, we're not going to bother writing the 2 minus, we're just going to write 2.
Yeah, and then you swap them.
Swap them, correct.
Oh, yeah.
And hopefully you can see that that's a much quicker technique than having to go through diagrams and seeing how many electrons are being given out. Okay?
Yeah.
As long as you can remember that. So now we're good, aren't we? So we've got Al plus Fe2O3 to give aluminium oxide. What's that going to look like? Aluminium oxide. Now that one could be tricky because obviously I've not been given, you're not told how aluminium is acting here. Is it acting as an atom with 3? So I'll give you a bit of a hint here. It's acting the same way as iron is. It's acting as if it's got 3 electrons on its outer shell.
Sure.
So it's behaving the same way as the iron was behaving here.
Would it be Al2O3?
You're absolutely spot on. And then, of course, over here, you'd have Fe for the iron, wouldn't you?
Yeah.
Let's try and balance the equation then.
Wait, let me write all that. Would it be 2Al plus Fe2O3?
Yeah, so 2Al plus Fe2 gives Al2O3 plus 2Fe.
Oh, yeah.
Correct. Okay. Now this is a scenario where you could be asked to write a half equation. So half equations can appear either in a case where you've been given a displacement reaction, or they can appear in a case where there's electrolysis that has taken place. So it's worth knowing the scenarios where you'd be asked to write half equations. So let's try and write some half equations over what has happened. All right. So if we look at this here, we have got aluminium. Now, for it to be able to form aluminium oxide, yes, and it's formed a bond, it must have lost electrons. Does that make sense, right? Now, because it's behaving as if it's in group 3, we're looking at the formula, how many electrons would it have to lose? Well, in either case, even here, the iron had to lose 3 electrons to form iron oxide, so it will also have to lose 3 electrons. So if we're writing the half equation now, we'd say the aluminium, and we're only going to focus on the aluminium here and what's happening on the other side. So the aluminium loses its 3 electrons, and when it loses its 3 electrons, what does it become as an ion?
Would be Al3 plus.
Well done.
Okay.
The easiest way to also know it is that whatever the number of electrons are here that are lost, that's the charge that goes over here as well. Okay. Yeah. So this here now is what we call a positive ion, also known as a cation. Yeah. Positive ion is known as a cation. And the reason why it's called a cation is because if you carried out electrolysis, this guy would go to the cathode.
Yeah.
Okay. Yeah. So that's what happens for the aluminium. Generally, what they like in your course is they don't like these minuses here. They want you to take it to the other side. So just as how you would tackle an equation with an equal to sign, something is negative and you move it across the equal to sign, the sign changes, doesn't it? Yeah. So generally, AQA want you to write it in this form. Not that this is incorrect. I don't know why they want you to stick to this convention. Okay, so just worth remembering that that's how you'd write the half equation. Now, very clearly here you can see that this has lost electrons. And what did we say? We said oxidation is loss. But also what can you see here? It's been oxidized as well because it's got oxygen. So whichever definition you take, you still clearly see that the aluminium has been oxidized. Now for the ion, well, the ion here, what charge did it have? It had Fe3 plus because it was behaving as an atom in group 3. So it had lost those 3 electrons. But now, for it to form ion, so if it had lost 3 electrons when it was as a compound, to become pure iron, what must happen? Well, it should gain back those electrons. Then it will be restored to the state of being just an iron atom. So to do that, it needs to be given the number of electrons it lost. So that 3 here has to be reflected here. So you need to give it back the number of electrons it lost, and then you can return it to being simply an iron atom.
Right.
Now you can see here that this is reduction because reduction is gain. Now the reason why I don't like this format here, and I know AQA, this doesn't make pure well, not logical sense, but it's not easy to see from here that you're looking at oxidation because you've got a plus sign here. So it looks as if you're adding electrons, isn't it?
Yeah.
Whereas this is very, very clear. You can see that I have lost electrons and this is my end result. So just be careful if you're asked to say, here is a half equation. Is oxidation or is reduction being shown? Be very careful, okay? So something like this would look like this is reduction, but it is not reduction because the final product is Al3 plus, whereas this here is reduction because the final product is actually iron. I'm starting off from Fe3 plus, which is a positive ion of iron, which has then gained 3 electrons. So that's the first instance.
So when you first like write it out for yourself without like swapping the sign because they want it like that, do you always start with the one that's on the
furthest end?
The first side.
They sometimes can be specific, but if they're not, then I would just suggest just start off from the first
So
line.
What would they actually ask as a question for this?
So for this question, for instance, they might ask you to say, write the half equation to show that the iron oxide has been reduced.
Oh, okay.
Okay, so write a half equation representing the reduction of the iron oxide, or write a half equation, or write 2 half equations to represent the redox reaction. So then you would label this here as you'd say, that's my oxidation, and this here is my reduction half equation. So far, so good? Okay. Now you notice something here. What doesn't feature? The oxygen doesn't feature at all. The oxide part does not feature in these half equations. You notice that. Yeah? So I'm going to give you one for you to just try it, and I'll give you the equation just to make life a little bit easy. So now we have copper versus silver nitrate. Now, a classic question that could come from this, oh, why is the board not? Now, this guy here is colorless, okay? And this metal, copper, is in chemistry described as being salmon pink, okay? So the question we're posed with first is, can such a reaction take place? Can such a reaction take place? So in other words, is copper above silver in the reactivity series?
Yeah.
It is. So a displacement reaction will take place. So you're going to get copper nitrate and you're going to get silver. So to balance this, we need the 2 there and the 2. Now this guy here is blue in color. So blue liquid. And of course, silver is silver. Okay. Silver gray. Now if you're asked, so this here is an example of a displacement reaction. The copper is kicked away the silver, and it's taken its place, right? So the question is, have a go at writing the half equation for what happens to the copper and also for what happens to the silver.
If copper's a transition metal,
yeah,
then is a charge like 2 minus or something?
It can be well, it's a metal, so it will always lose anyway.
Yeah.
But it can sometimes lose 2, sometimes it can lose 3 electrons. Okay. Now, not very easy to tell what's happened, is it? Is it? It's not very easy to tell. Now, your hint here would be to look at this nitrate part here. Now, this is an example of what we call now, there's some ions whose charges you need to know and memorize. So which are these ions? These have to be memorized. These have to be memorized. They will not be given to you.
Oh yeah, I think.
So you've got nitrates, NO3 minus. Okay, so it's got a charge of -1. So we just write minus, NO3 minus. Then you've got SO4 2 minus, which is a sulfate. So it's got a charge of 2 minus. Okay, so nitrate, sulfate, and you've got another one, which is a carbonate, which has got a charge of CO3 2 minus. And then you have ammonium, which is NH4 plus. These you absolutely need to memorize. So that's a nitrate ion, sulfate, carbonate, ammonium. Okay, so just to give you an example, imagine I wanted to write the formula for, I wanted to work out the formula for potassium nitrate, or we'll just make it easy, for calcium nitrate. So we write our calcium and we write our nitrate. Now, what's the charge on a nitrate ion? Well, we're just going to be concerned with the number. We don't have to worry about the sign, whether it's positive or negative. So it's 1. You happy?
Yeah.
What about calcium?
2.
2, correct. And what would you do next? Swap.
Just put it in bracket. Oh,
yes, you're right. It has to go in brackets because it's this 2 applies to everything here, not just the oxygen. You're absolutely right. So this would then be CaNO3 2.
Yeah.
So when you look at this formula now, can you, if I had to ask you, well, what's the copper behaving like? Is it behaving like something in a group 2 or group 3? Just by looking at this formula now, what would you say?
Would it be behaving like something in group 2?
Yeah, it's behaving like something that's got 2 electrons. So because if you remembered this, then it becomes easy to decipher what these transition elements are behaving as. All right. So I'll give you a little piece of homework to make sure you have these memorized for your upcoming exam. So you got that?
Yeah, I've got them.
Okay. So what do you have then as your first half equation for what's happening to the copper?
Wait, what first. So
we're going to write half equations for what's happening from going from the left-hand side to the right-hand side, just for the copper first.
So first it would be Cu and then would it be plus 2E minus?
Plus 2E minus? Okay. So let's think a little bit about what we have. Here what we have is a copper atom, isn't it?
Yeah.
And it's got 2 electrons in its outer shell.
Yeah.
Yeah. Whereas here what I have is copper ions. So to go from a copper atom that's got 2 electrons to go to a copper ion, what do I need to do to this copper atom? Do I need to add electrons or remove electrons?
Remove.
Correct. And how do I represent removal? The minus.
Yeah.
Yeah.
So Cu minus 2e minus
Good.
equals, would it be Cu Cu2?
So whatever that number is here is a number that goes there as well.
Yeah, so C is it plus?
Correct. General thing to remember, I know there was a little bit of a puzzlement there. Do I put a plus? Do I put a minus? Yes.
Yeah.
All metals form pluses
Right.
because they all lose electrons. So
Yeah.
as long as it's a metal and it's lost electrons, it's got to be a plus. It will never ever be a minus.
No.
What about non-metals? All non-metals gain electrons. So whatever the number of electrons gained is the same charge that you put as well. Okay. So this is what happens to the copper. Very good. Now you can see here that is it being oxidized or reduced?
Is it oxidized?
Correct, because oxidation is loss. It's lost these. Very good. The next part then for the silver.
For the silver, do I just what do I write that as on the? Do I
So
write
let's
it as
think. Yeah, and that's very, very good questions you're asking there. So let's think about the silver here. It's a metal. We know it's a metal.
Yeah.
Is it behaving like a group 1 or a group 2 or a group 3 metal? What do you reckon? Just by looking at this formula.
Would it be a group 3?
So look at what it's joined to. Forget about this number for now, the 2 in front of it. Just look at this formula, AgNO3. So this is the nitrate ion.
Oh, wait, nitrate. I thought that. So nitrate is a.
So nitrate is the one that has to be memorized. Nitrate always behaves like it's a. You have to take it as a whole thing. See how we were finding the formula for calcium nitrate?
Yeah.
We wrote NO3 So if you are finding the formula for silver nitrate, which we are given as AgNO3, how did it end up at AgNO3? Only if I had a 1 on Ag. Yeah. Because I know our orders have a 1 always on the nitrate.
Oh yeah.
Only way I can end up with AgNO3. It must be behaving like something in group 1. That's why these are super important. Because if you can remember these, then you can work out what these metals are behaving as when it comes to displacement reactions. Okay. Yeah. So it's behaving as a group 1. But here, remember, it's in the form of, is it in the form of an ion or an atom when it's in silver nitrate?
Is it an ion?
Correct. Because here it's behaving, it's in atomic form now, so it's as an element. Yeah. So what do you reckon it would look like for the half equation going from left to right?
Would it be? Would it be Ag minus?
Okay, so remember silver is a metal, so all metals form
Ag plus.
Correct, well done. All metals, as long as it's a metal ion, all metal ions are positively charged. I'll put a little point here for you to remember as well. All metal ions are always, there's no exception to that, are always positively charged. And all non-metal ions are always negatively charged. The key word here is ions. It has to be an ion. This is not all metal atoms. This is all metal ions, meaning because they have lost electrons, they will always be positively charged. They'll always have more positive stuff, more protons than there will be electrons. Okay?
Yeah.
Very good. So Ag plus, well done. And what's the next line? So it's gone from an ion and it's now formed an atom. So what happened to it then for it to go from an
ion? Arrow, is it Ag?
Ag?
B minus E minus.
You could write it like this, you're right, absolutely. You could write it like this, or just think about what's happening. I have an ion of silver, Ag plus. If this receives 1 electron, because initially to form Ag plus, what did it do? It had lost an electron, so I've got to give it back. Yeah. So whenever you're writing, it's almost thinking about it in reverse kind of thing, but if that kind of makes sense. So then you'd have Ag outside. But this here is the same. Now what AQA want you to do, of course, with this, they would want you to put the -2 over that side, okay? And they would want this -1 electron on the other side. In other words, they always like to see the electrons being plussed. They don't like to see electrons being minused. So does that make sense?
Yeah. So yeah. Is it Ag plus?
Yeah.
Plus E minus.
Plus one electron received, good. Gives Ag, absolutely, which is Ag.
With the electrons. With the electrons, do I have to put the 1 in front?
Generally good practice, because what would generally happen is in your exams, they will leave this part with a dashed line.
Oh, okay.
They'll normally leave it like that.
Yeah.
But they'll put E there, but they'll leave that blank.
Yeah.
So if it's a 1, then explicitly make sure you write that it's a 1.
Yeah.
That makes sense. Okay. Yeah. Good stuff. These are pretty tricky concepts, I think, when it comes to ionic equations. So let's not fully rush. We do have time to really become very good at this stuff. Now let's try and see if we've got a few questions. Okay. One more thing, actually, before I go on to move to the questions, because this is something that they could ask you. So they might ask you to write the overall ionic equation or the half equations. Now, the overall ionic equation is easy. So imagine that asked you for this particular reaction to write the overall ionic equation. So what you do is you write out everything as it is in, yeah? So Cu is just Cu plus, well, here, if I look at this, I need to split this up into its ions. So I've got 2Ag plus, and I've got 2NO3 minus. And over here, I need to split this into its ions. I've got Cu2 plus, and I've got 2NO3 minus, plus I've got 2Ag, which is the last thing. Then to write the overall ionic equation, anything that is the same on the left-hand side as the right-hand side, I cross it out. So what can you see that's the same? Well, 2NO3 and that 2NO3. So the overall ionic equation, running out of space here. Okay. So overall ionic equation, sorry, it's on another page here, but you remember
is
what...
is this what the spectator ions is?
Yes.
Oh, okay.
Absolutely spot on. So that's what we call the spectator ions, because they are, nothing happens to them. They're in the same state, both on the left-hand side as well as the right-hand side. So we end up with something that looks now saying Cu plus 2Ag plus, which gives 2Ag plus Cu2 plus. Yeah, so this is what we call the overall ionic. So worth looking at the wording. So all the spectator ions have been removed. Now the next part, of course, is from here, you can now start writing your half equation. So sometimes, Rahil, it does help to write the overall ionic equation before you start doing your half equations. So the half equations are going to involve, how did I get from Cu to Cu2 plus? And how did I get from 2Ag plus to those 2Ag? Now here, because there are 2's on both sides, when you write your ionic equation, you don't need to involve this 2.
Yeah.
So you could just say Ag plus, yeah, plus 1 electron received gives Ag. You don't bother with the 2 there. That's for the half equation. And the Cu, of course, they always like it with pluses, so you're going to have to say Cu2 plus 2 electrons. Okay, so these here are what we call half equations. So far, so good?
Yeah.
Okay, good stuff. We haven't quite made a start on electrolysis, but it's okay. Don't worry too much. We will go through it. This was giving us some good foundation elements that you need, which are going to play a big part when we start looking at electrolysis, especially this idea of half equations. Because if you start understanding them from displacement reactions, it becomes much easier to understand them from an electrolysis point of view as well. Yeah, great stuff. Right, not going to go into many questions, but what I'll do, Ricky, is I'll send you some practice questions, focusing on half equations maybe, and overall ionic equations. Just have a go at that, because that's what I want you to build your expertise on. There won't be many, but worth definitely you having a go. Now, I am available all day tomorrow. Do you have any preference for what time you'd like to start tomorrow?
Wait, what day is it tomorrow? Thursday.
Tomorrow is Thursday. Yeah, you got football tomorrow, haven't you?
Wait.
Do you have football tomorrow, or do you have any activities going on?
I'm trying to think now. I can't even remember.
All right. Do you want to have a think and
okay.
then text me maybe sometime in the course of the evening?
Yeah, okay.
Is that all right?
Yeah, that's fine.
Yeah, good stuff. Right, I'll send you the video recording of this as well, and the board work, and I'll send some additional questions just for you to start having your go at half equations. Nothing particularly time consuming, so you should be able to run through them before we pick up pieces tomorrow at some stage. Okay.
Yeah.
Good man. Nice one, Rahil. You have a lovely evening, and I shall be seeing you tomorrow.
You too.
Thank you. Cheers. Bye-bye. Bye.
Bye.
Cheers.